All right, so this work represents a sort of ongoing attempt that from the outside might look that I'm trying to combine the best of symbolic approaches and find a sort of middle way, but actually I'm trying to annoy both sides of these debates, so here we go. So the problem I'm going to be talking about today is the problem of learning language from positive examples. So from a finite sample of sentences from an infinite language, we want to learn a finite description, grammar of that language. Now, of course, we know for a long time that doing this even in a really restricted class of grammars is a really, really hard problem. And also, since we're celebrating here 60 years of perceptrons, we want to do this with a sort of perceptron-style learning. So we need to have some kind of error signal, or loss function that we're going to be optimizing here. And fortunately, we're going to solve sort of both of these problems with two birds, one stone. Our stone is going to be distribution learning, that is density estimation. So our loss function is going to be, I'm going to use the linguistic term here, the surprisal of the next word given the preceding words that's assigned to the model assigned by the model. So what we're doing is we're going along, we're predicting the next word. And now this is equivalent, of course, to maximum likelihood estimation. This is also in the sort of neural net literature called cross entropy. The cross entropy objective, these are all exactly the same things. But basically, this is just the standard language modeling objective. Now, for the many linguists here in the room, the hypothesis that links probability and grammaticality, sorry about that, or acceptability is quite non-trivial. There's been some interesting work by folks like Alex Clark and Shalom Lapin who have tried to look at some of these things. But for now, we're not going to worry about those issues. We're just going to say we're going to be worrying about modeling these distributions. Okay, and so I'm going to talk, my starting point is going to be recurrent neural networks. I'm not going to take a particular stance on which variant of recurrent neural networks. In general, I'll be talking about LSTMs, which are probably about the most general purpose good learners that we've got out there. If we look, say, on a standard language modeling task, where we give a finite sample of data and then we evaluate the model's predictions on a held-out sample of data. We can evaluate this using the exponentiated average surprisal, which we call perplexity, which has some nice sort of intuitive interpretations. But what we see here is the model that was sort of state-of-the-art roughly just a couple of years ago gets a much higher average exponentiated surprisal than an RNN that you can train in a matter of minutes on a laptop using sort of standard tools. And okay, so right, but we aren't excited about neural networks these days just because our perplexities are better. We're excited about them because of all these really cool applications that people at Google are deploying and making our lives better with. So we've got here on the left this speech recognition system where they're now able to using an RNN-based transcription system, get a word error rate of 5.6%. This is somewhere around human level performance. Now there are a bunch of ways one can quibble about this particular data set, but it's impressive. We've got machine translation. This is a problem I worked on for a very long time. What the bottom line is with RNNs is just doing incredibly well. And so these things are really seeming to learn a lot about very hard problems in language. But I want to talk about maybe some problems with RNNs as models of language. So the first thing that we might remember is that RNNs are actually given enough capacity, Turing complete. So they can simulate a Turing machine with finite tape. If you want to make the tape bigger, you make the capacity of the neural network bigger. And of course, those of us, who worried about the, Peters and Ritchie results, saying, oh my God, transformational grammars are equivalent to Turing machines. This is bad. We can't, learn anything if we've got such powerful learners. But we're going to take a sort of, we're not going to immediately give up on them. So we're going to look. We're going to say, well, do they make good generalizations anyway from finite samples of data? Maybe they just don't use all of that excess capacity. So what we're going to be focused on in this talk is what are the nature of the inductive biases that recurrent neural networks have, And then we're going to introduce a variant of recurrent neural networks for natural language called recurrent neural network grammars that are going to have more appropriate biases for learning natural language. So let's start by talking about recurrent neural networks and what their inductive biases are. So first I'll say understanding the biases of neural networks is actually a really hard problem. We can't actually even describe what they do very well in terms of single models, and I'm now trying to say we should talk about what they do in general. So this is a really hard problem, right? But I think there is a lot of evidence that they prefer sequential recency. So first we can do a simple functional analysis, and we can show that gradients become attenuated across time. So that basically means that the number of intervening steps in an RNN that the gradient has to travel, we're generally going to see the magnitude of the gradient to representations or events that happened earlier on decreasing exponentially. So this is a big problem. And yeah, these other variants, these fancy things, LSTMs, GRUs, all of this stuff, they help, but they still forget. And there it's not so much maybe gradient attenuation as gradient noise. You have other things sort of overwriting the memory in those as time progresses. At any rate, the problem is you basically just have these linear length dependencies somehow trigger forgetting. The second thing is we see in practice people do all sorts of funny things to make RNNs learn better. So they'll do things like reverse sequences when they want to map one sequence to another so that at least some of the material is close by in linear order. So there's clearly some there's this in this original paper where they show that machine translation could be well solved with RNNs. They found that the biggest single improvement they could make to the system was if they reversed the input sentence when they read it into the RNN and then started translating into the target language from the left. So basically, the beginning of the first sentence was close to the beginning of the second sentence, and this was very helpful. So the average distance between words, assuming these two sentences had monotonic orderings, was the same distance in both versions, but at least some of the words were close together. So we again see a bias for recency. So the third thing are, we have innovated in neural network land and imposed techniques that let us create more direct connections that go further back in time. So one of the famous examples of this are these attention mechanisms, or what we call in neural network land attention, which is basically just a direct connection to a point further remotely, further back remote in time. And these things make a huge difference. So by solving this kind of recency problem, we do better on these tasks. And then finally, this paper that I've been very excited about by Tal Linson, Emmanuel Dupuy, and Yoav Goldberg from a year and a half ago showed that subject-verb agreement is not, we don't see a very good pattern of the kinds of errors that RNNs make. And I want to review these results a little bit because we're going to look at this and see how they do with standard RNNs and then also with sort of innovated RNN. So the task that the construction they're interested in is looking at the agreement between subjects and verbs in the English present tense. And so obviously if you've got a simple sentence like this where the subject is right next to the verb, RNNs are going to be ideal. You're going along, you're predicting the next word. The thing you've got to predict is very salient to the model. But of course, because we can embed things sort of arbitrarily deep and get still perfectly comprehensible sentences, we have to worry about constructions like this where there's a lot of intervening material that doesn't actually need to be attended to when you're making a decision about what that verb form is. Now, of course, we know that humans tolerate a certain number of errors. This is well studied, but what Linson et al. Show is that, well, you actually do much worse than you would expect. Okay, the other thing to notice is, so basically the number of attractors that you have between the target and the verb are grow sort of linearly with linear. So we've got down here already 7 hops we've got to make. And their big result is this. where you see, the x-axis here are the number of attractors, and then the y-axis is the error rate according to different models at deciding the correct form of the verb, given that prefix. And with a model that's trained using a language modeling objective, so again, just the standard surprisal objective that I started out with, it does terribly. It makes a huge number of errors. Now, this is on a fairly small data set and a fairly small neural network, but they also replicated this finding on this billion-word Google-sized data set, something that I would have trouble training, even though I work at Google. Basically, what they're finding is that these models appear to be getting distracted by these attractors. This is what the psycholinguists look at and say, how often does this happen? Well, it maybe happens 10% of the time. Here it's happening 70% of the time. This is not natural. Now, obviously, the perplexity of this model is brilliant. And this, I think, gets back to a point Sharon made yesterday morning, where she said, well, NLP people are very happy when we do well on the average case, and linguists are very concerned with how well we do in the sort of rare, sort of long tail phenomena. And I think, though, if we want to take serious, when I put on my hat as an NLP person, I also really need to be concerned with this, because it's not okay to have a system that sort of only works when it has no intervening material between the subject and the verb. So I want to solve this problem. And I also, since we're here to celebrate 60 years of syntactic structures, now Chomsky didn't really say this in syntactic structures. I went back and read most of it last night because I was jet lagged. But sequential recency is not the right bias for learning human language. I think this is, if there's going to be one robust claim that he's been making for 60 years, it's going to be that one, right? So structure dependence. Let's put some structure into the model. That's going to be my solution. So the proposed solution, and actually my group at DeepMind has been working on several different strategies for this. I'm going to talk about one of them with my former student Adi Kankoro, who's now my colleague at DeepMind. These are called recurrent neural network grammars. Basically what we're going to do is we're going to generate symbols sequentially using an RNN, just like we always do. But we're going to introduce some control symbols. And these control symbols are basically going to be forming constituents. They're occasionally going to compress a sequence of terminal symbols into a constituent. And so rather than having, say, a sequence of 10 words on, in the stack, we're going to say, oops, all of those 10 words get reduced together, and they're going to be represented by a single complex symbol. And the RNN is going to just alternate or predict either terminals or control symbols based on the history of compressed elements and non-compressed terminals. And we're going to use a top-down, left-to-right generation of the tree and sequence. This has certain nice properties. You can use other build orders. You can do bottom-up. You can do left corner. We'll probably be writing a paper about some of these other alternatives at some point. But let's start with the top-down derivation. Just let me show you what this looks like. So we're going to build the sentence, the hungry cat meows loudly, and we're going to do it as follows. So we're going to have a set of data structures. So one data structure called the stack. We're going to predict an action, and then there's going to be a probability associated with it. So the action we're going to start with is one called non-terminal. This is basically going to open a parenthesis with an S symbol. And we're going to do this with the probability of having an S at the top of a tree. And then that's going to update this stack data structure by basically pushing this S on top. Next, we will, to derive the sentence, we want to generate an NP. We're going to do this conditional on the previous things that we've done. We don't want to sort of forget anything yet. We don't want to make any independence assumptions, that is. Now we're going to start generating some terminal symbols, build the contents of this NP. We'll call it the hungry cat. And now what we're going to do, we've gotten to the end of this NP. We're going to now execute an action that is going to close this non-terminal symbol. And this is sort of in the standard world in an RNN, we would just put a right bracket there. But what the RNNG is going to do is going to say, okay, now I know that I can I can pop off of the stack enough material and build a constituent. So I'm going to replace this stack configuration with this one where we've got a single symbol representing the bracketed NP, the hungry cat. And then the derivation will continue, and eventually we're going to be left with a single constituent on the stack, which is going to represent the whole sentence, and that's when you know the sentence is over. Okay, so what are these probabilities here that we want to define? So a couple of things we can show first. First, all valid tree string pairs are in a bijection to valid sequences of actions, so we can't do things like close parentheses that aren't open, and we can't close empty parentheses, although you could imagine that variant. The second thing that you can see with a little focus is that every stack configuration perfectly encodes the complete history of actions. So therefore, we can decompose the probability as follows. So we can say that the joint distribution of a tree and a string of terminals and a particular tree y is just the actions that the sequence of actions, the probability of the sequence of actions. And then we can use the chain rule to say, well, we're just going to model the subsequent action conditional on all of the actions that came before. And then we can also invoke the second proposition here that says the probability of an action at any time is just conditional on that stack structure that we're building, because that stack perfectly encodes the history of actions. So basically, our task as a modeler then is to model the following probability distributions, conditional distributions. So given some stack configuration that looks like this, define a distribution over the possible structure building actions, which will be these non-terminal or generate or reduce actions. So what are the challenges we face here? Well, first, we've got unbounded depth, so sentences can be as long as they want. So we better be able to deal with very long things. So when we have this, well, the first thing we do is think, well, recurrent neural networks are a great way of dealing with sequences of unbounded depth. So we just read this from left to right and then take the final, so H4 in this case, as the representation of the contents of that stack. The second thing to notice is that we can have arbitrarily complex trees, so we're going to be nesting these things inside of each other. So here we can use recursive neural networks. There are a whole bunch of different ways of defining this. The way we define this as follows. So we saw how to build a representation for, so let's consider building the representation for the hungry cat. What we're going to do is we're going to use an RNN to read the daughter nodes from of this NP from left to right, but we're going to start by reading a representation of the constituent type. So we're going to go from left to right and then close this and then take that representation as the representation. But actually what we want to do is we want to do this in both directions. Bidirectional recurrent neural networks tend to work a little bit better. We're going to start again with the NP symbol on the right side and read that first. The idea is to tell the RNN what is it you're going to be looking for. So if we take the notion of headedness seriously, the RNN sort of wants to extract features from one of those words probably. And so we hope this helps it do this. We take this again, and then we add these two representations together. This gives us a vector embedding. Now the cool thing about this is in the same space as the lexical embeddings. So if we have a sentence, or if we have a constituent like the very hungry cat, we just know that very hungry as an adj will be also represented by some vector, and we can continue to define these things as follows. We solved the arbitrarily complex trees thing. The final thing to note, and this is really an algorithmic thing that just makes this work fast, is that when we execute one of these reduce operations, so imagine we execute reduce here, we're not going to have a completely different stack configuration. There's a lot of shared material between these two stacks, and we just don't want to have to replace that much material on all of these things. So a couple years ago, I had a paper that showed that you can do all of these stack manipulations very quickly using a data structure called stack recurrent neural networks. And so we do this, and this makes this a fairly fast model. So let's talk about what the inductive biases are for recurrent neural network grammars now. So if we accept these two propositions, first, that RNNs have a bias toward sequential recency, which I think I convinced you at the beginning, and second, that syntactic composition learns to represent trees by heads. We have some nice empirical evidence for this that you can read a paper by Adi from EACL this last spring that looks at this. If we have those two things together, then we can conclude that RNNGs have a bias for syntactic recency rather than sequential recency, which is kind of what we wanted to see. So let's illustrate this. So what this headedness proposition means is that this NP is going to be represented by something like a representation of the word keys. And then to predict this verb down here, well, we've got to predict, VP, and then we've got to predict the verb. So there are sort of two hops. Now, if we introduce, so there are two hops. Now, of course, there's just one hop in the RNN case, so we've actually got a little more work to do here. But when we start looking at bigger material, we see that we're still going to be representing this when there's that PP inside of this NP. We're still going to be representing this by keys, because this is just going to be kind of elided by that composition function in favor of its keys. We still only got two hops, whereas down here we've grown to four hops. As things get bigger, we stick with two hops always in the RNNG case, and we keep growing sort of linearly in the regular RNN case. So basically, RNNGs need a constant number of hops to sort of know what to predict, whereas RNNs need a linear number. So I think this is a better bias. Okay, so we can evaluate these things in a bunch of different ways. I'm going to just stick with this kind of average exponentiated surprisal for a while. So here's that data set we started with. And if we look at how well recurrent neural network grammars do, they drop down to a little bit. So this is a nice reduction in perplexity. I will say, computing this average surprisal under recurrent neural network grammars is a non-trivial computational problem. We don't have a nice dynamic programming algorithm to marginalize over all of the trees anymore, but it's doable. The second thing we're going to look at is Tal's experiment on how well we do at predicting the right form of the verb, right? And what we're going to see here is that at the beginning, RNNs do a great job of predicting the right morphology of that verb. But as the number of attractors increases, we start doing better with RNNGs. So it's in that long tail of phenomena where you really have to, where there's very little evidence for what the pattern is in the data, that you need this extra inductive bias to do well. Now, the final thing I want to say here is that we might just say, well, hold on, you're putting a bunch of extra syntactic information into the model. Maybe that's all that you need to, maybe that's the concern. So what we did is we trained an RNN on that sequence of actions. We didn't give it a composition function, but we did give it that knowledge of syntax. And we find that that doesn't work well at all. It basically just distracts it. It does actually a pretty good job of predicting trees, but it isn't learning good representations of sentences. Okay, so I'm going to end here. Let me summarize sort of where I think we are and why I think inductive bias is important, and why I think maybe computer scientists can might have some interesting things to tell linguists. So first, what are the strategies that we see in the literature? So the standard approach taken in generative linguistics has been to restrict the hypothesis space. And this is a great way of inducing bias. Like, we all love linear models, we all love reduced hypothesis space, it's great. But there are a bunch of other things that basically are coming out of, I'd say, more the machine learning literature, and also can solve these problems. So we haven't sort of said you can't represent things, we just say you're unlikely to represent things. So we've got priors and regularization. This comes up in the Bayesian literature. We have certain kinds of input transformations, and then I think what neural nets are doing is really exploiting things like gradient flow. There are a couple of interesting questions. We're observing trees here, and maybe we can start incorporating more interesting transformational actions, just in the spirit of Chomsky 1957. Well, these are just phrase structure trees, but what about those transformations? Well, we can put those in there maybe. So thanks, and I'll take maybe one or two questions.
All right, so we have 5 minutes for questions before we move to the general discussion. And please remember to say your name and affiliation at the start of your question.
Hey, Nathan.
Nathan Schneider, Georgetown. Has you or anyone else started thinking about CCG grammars in this framework?
Started thinking about it, yeah, but haven't started doing it yet. There are some interesting questions there, just because those bring semantics in a much more they bring semantics in, so deciding how to do we condition on the semantics? Do we jointly model semantics and the sentences? Makes the model that you need look very different.
So, following up on the last thing you said about transformations, you had this paper with Tim Hunter about a probabilistic implementation of minimalist grammar. And so I'm wondering whether there is any potential relationship between the work that you did in that and things you could do with this stuff.
Yeah, I mean, basically it's fairly non-trivial to implement transformations. Anywhere you've got sort of a clear set of actions that can be defined. So one of the great things that I originally had in this talk, but had to take out due to time pressures, was how you do inference and parsing with these things. And so in the old days, we wanted to have one grammar that kind of did everything, and we had sort of a generic inference procedure that figured out, given a sentence, what the most likely parse or what the parse was. This involves having a complex grammar that is too difficult to directly do inference in, but you jointly train with that grammar a recognition model that says, given a sentence, what actions do I think were used to build this? And you get a distribution over trees. And so you actually have a lot more flexibility to do interesting things in, so one of the problems with minimalist grammars or stabler grammars are, the inference algorithms are, they're there, but boy, they're kind of hard to work with. And we now can sort of think about getting rid of those entirely and just building the models that we want using this sort of paired grammar and parser set.
I have a question, because I think I missed this. What does your training data look like? Where are
Oh,
the
good,
trees?
good question. These are the training data are the trees. So this is actually the Penn tree bank that I trained this on. So of course this is a generative model. There we have a joint model of trees and strings. We can train this with EM, marginalizing out those trees. We haven't done that yet. I think there we're going to face some really hard problems. One of the things we see with neural nets is they're happy to learn anything, including noise. And so if you think about what EM does, it alternates between sort of saying, I assume the model is right, now I'm going to label a bunch of data, and now I'm going to learn from it. And that first pass where it labels a bunch of data, it's going to say, all right, I'm going to fit that. And so the standard models we use to do unsupervised grammar induction, they have much stronger biases than this. So doing unsupervised learning is, yes, that's also ongoing. Yes.
Geraldine Jean, Johns Hopkins. This may be a question for the general discussion, but can you articulate what the differences are between this kind of approach of embedding structure in your network and the approach that Paul Szymanski was talking about yesterday, namely TPRs?
They're really rather orthogonal. So we have a lot of flexibility in defining that composition function, and you could certainly be using basically a tensor product representation of the sentence that's getting built as you're constructing the sentence. So when you make a decision about what the next word is, it's going to be conditional on a tensor product representation of the prefix of the tree. So actually, sitting in Paul's talk yesterday, I was inspired to start thinking about what that would look like precisely. So.
One more.
Paul, yeah.
So one of the non-linguistic aspects of using RNNs, it seems to me, is the feeding in one word at a time aspect of it. So when we do syntax, that's not how we do syntax. And to what extent do you think the picture would change if you had a way of presenting in parallel the whole sentence in such a way that you could deal with different sentences? But how much does that change the way?
Well, I mean, the most obvious way of thinking about that would be with a, what they call an undirected model or an energy-based model. I mean, it's a little bit like the RVMs, you used to, you work with. The problem there is really, that solves actually a lot of problems. You get, or at least in the conditional case where you're learning that parser, you have there's some bad biases in the conditional version of these things that go away. The inference problems become really hard, so computationally, that's in terms of what I can do to implement this, I don't know how to deal with that right now. But I mean, in the sense that this is something that is one of the places where the sort of gap between kind of this is a model of cognition and this is just a tractable model I can work with is quite wide. So this one sentence at a time thing isn't the greatest. Or one word at a
So I
time.
want to now switch to the general.
No, that's backwards. You should give the other answer.
I was going to give your answer. John, do you want to give the appropriate answer?
So no, actually it's Chris who has been standing on the higher ground here, and his model is left to right. And you're absolutely right, Paul, that it might be better to look at the whole sentence and do a kind of pattern completion. That would make a lot of sense. But I think your answer to that part was we don't know how to do it properly.
Thank you,
Thank you.
Chris.